Hi everyone, thank you for listening to this talk. I'm Luisa Lucie-Smith and I'm a postdoctoral research fellow at the Max Planck Institute for Astrophysics. And first of all, I want to thank the organizers for inviting me to give this talk and for putting together this wonderful conference. And today I'll be telling you a bit about machine learning, applications in cosmology, and in particular focusing on explainable machine learning methods that have been the focus of my own research. So machine learning has been now used and successfully used in a number of applications in cosmologies. And these include, for example, automation tasks. So for example, processing large volumes of data from upcoming surveys now requires a shift from manual intervention to automated techniques for many different data analysis tasks. These include, for example, classification tasks like transient classification or different galaxy type classification tasks, also regression tasks like, for example, estimating photometric redshifts, and even clustering or outlier detections where we can try to detect rare outlier objects in the sky that cannot be well described by our own models. Another applications where machine learning has been particularly successful is in acceleration. So most of our cosmological analyses inference pipelines require computationally expensive cosmological simulations. And so machine learning has been used, for example, to try to emulate the output of those computationally expensive simulations with machine learning. So starting from some training sets or a number of examples of outputs of simulations from the initial parameters, machine learning can basically do a sort of form of interpolation, so emulating what the outputs of the simulations would be for different points in that initial parameter space. And so the community has been building many different emulators for example, summary statistics of the logical structure. And these include, for example, emulators of the matter or the CMB spectra, like it's done by the Cosmopower set of emulators led by Alessio Spurio Mancini and Davide Piras, who basically are able to provide very, very fast CMB or matter spectra starting from your cosmological parameters. Similarly, the Baco team has been developing emulators. Here's just an example of an emulator for the matter power spectrum that you can see can reproduce basically the n-body simulation spectrum very, very accurately, or even emulators for the halo mass function. So this is an example from the Emulus team, where again, starting from a broad range of cosmological parameters, you can get very, very fast predictions for these summary statistics, such as the halo mass function. And there are many, many more of these sort of emulators, and people have been going even beyond these summary statistics in providing emulators even at the field level. So for example, starting from the full 3D linear density field, which is very cheap to evaluate, and then training an emulator to produce as output the nonlinear density field, or the displacement field of the nonlinear gravitational evolution. And this is work done by Drew Jamieson that was further extended by Ludwig Döser, who's a PhD student in Stockholm. And here basically they show that this field level emulators can reproduce the correct statistics of the fields much, much closer to the true n-body power spectrum or reduced by spectrum compared to other gravity approximate methods such as LPT or COLA, which you see start diverging from the true n-body power spectrum or reduced by spectrum at much smaller k than in the case of the emulator. And so these kinds of emulators can now be integrated within cosmological parameter inferences to get very, very fast predictions, either for summary statistics or even for the full field level. Another interesting application that I'm personally very excited about of machine learning cosmology is implicit likelihood or simulation-based inference. And this is basically a new parameter inference paradigm that differs from the standard likelihood-based analysis, because one does not have to explicitly write down a likelihood. And so this is very useful for situations where the likelihoods become so complicated that they become intractable to write down explicitly. And so thanks to machine learning methods such as neural density estimators, you can now perform parameter inference without the need to actually explicitly write down the likelihood. So how does this work? Very quickly, in a nutshell, what you need is essentially, instead of this explicit likelihood form, is a forward model. It's a forward model that maps your parameters, for example, your cosmological parameters, to your data, or more often it's really summaries of the data if the data is very highly dimensional. And so what you want is to basically have a forward model that maps parameters directly to the data or to the summaries, and so that you end up with basically a bunch of parameter data simulated pairs, which are these blue scatter points in this toy example, where, for example, you have one parameter on the x-axis and one dimensional data vector on the y-axis. And then what you do is that you can use neural networks or neural density estimators to learn this joint posterior of your parameters and your data vector t. And then you can take a slice through the observed data point, which then gives you your target posterior, so the probability of your parameters given your observed data. And there are different ways of doing this density estimation. This is an example taken from the PyDelphi package from Justin Alsing. And these kinds of methods have already been applied to full cosmological inferences, like, for example, in cosmic shear analysis with kids, in this example from Lin et al. In 2023. Again, with trying to learn the likelihood from this simulated data and cosmological parameters pairs, in this case using PyDelphi. And what they've shown in this paper is that the simulation-based inference is competitive with the standard NCNC analysis, and therefore can be trusted as this new kind of parameter inference paradigm for cosmology. And many people, like the ones I mentioned in these references here, have been trying to apply these simulation-based inference techniques to different cosmological analyses. And so just to summarize, I think machine learning is particularly successful at these kinds of applications where you're trying to automate or accelerate or trying to learn some probability distributions from sort of starting from known physical models or known forward models. So can we actually go a step a little beyond this and say, okay, we've got this method that can learn very complicated nonlinear patterns from your inputs to the outputs. Can we actually try to extract some new knowledge about the underlying physics from these deep learning models, if we can interpret their inner workings and how they reach their outputs? And this requires a slightly different class of machine learning models that goes under the umbrella of explainable AI. And so the issue with these explainable AI, with explainable AI, is there's basically this anti-correlation between being interpretable and the predictive power of these machine learning models. So you can, choose a very interpretable model, like a linear regression one or a decision tree, but then you're stuck with either a linear relationship between your input and output, or a simple binary decision to reach your outputs. On the other hand, if you go to the most predictive models that we have, which are deep learning neural networks, convolutional neural networks, which are the most powerful because they can actually automatically extract the most important features from the raw data. This kind of predictive power actually comes at the cost of often millions of parameters, meaning that you end up not actually understanding what the features are that the neural network is extracting and how the neural network then maps these features to a given output. And so then these networks with so many parameters and such complexity go under are often treated as black boxes. And so, at least in my view, there are really two requirements to for this explainable to reach this explainable AI method. One is interpretability. So this means trying to account for why the machine learning model reaches its predictions. So try to dig into the network and trying to see what features is the neural network learning, and how can I make sense of how these map onto the final predictions. The second one is explainability, which is actually trying to then map this account onto existing knowledge in the relevant science domain. So it's basically not enough to be able to tell you, okay, look, in the second layer of the neural network, the algorithm is learning this sort of pattern or this other kind of circular pattern, if then I can't map that pattern onto something about the physics that I'm trying to explain. So you need both the interpretable part and then being able to map this interpretation to the relevant science domain. And I just want to point out that actually many physical models in cosmology that we currently use are also not explainable. And two of these examples are, for example, halo density profiles and the halo mass function. So although these are summary statistics of the logical structure that have been empirically established through numerical simulation, actually it's still very hard to understand how these properties emerge from simulations and understand and gaining a solid theoretical understanding of these properties. So for example, in this paper here by Wang et al., they showed that basically the shape of the halo density profiles tend to be very similar or universal across even 20 orders of magnitude in halo mass. And although, you know, we can see this and establish this through some numerical simulations, we still don't understand the origin of this universal shape for the halo density profiles. On the other hand, for the halo mass function, we have a nice theoretical framework which tells us that we can map for many different cosmologies the number density of halos, so the halo mass function, into a single curve if we express it in terms of the mass fluctuations sigma. However, we see in simulations that the halo mass function actually exhibits deviations from this curve, and again, the theoretical understanding of the origin of this non-universality, in this case, in the deviations from the universal predictions, are still to be understood. And these kinds of theoretical questions are challenging to explain and to understand from simulations alone. So I want to give you some examples of how we've been applying these machine learning models, explainable machine learning models, to halo density profiles. So this is work that we started with Susmita Adhikari and Risa Wexler, where we started thinking about, okay, how can we build some theoretical foundation behind what determines the final structure of clusters. So again, we see in simulations that clusters form from highly nonlinear dynamics. You have smooth accretions falling into the halo, as well as violent mergers with other structures. And so what is really, how can we understand what through this whole highly nonlinear dynamics, what determines, you know, the final structure of massive galaxy clusters in simulations. So in this case, what we wanted to do, because we were interested, again, mainly on the interpretability part, we wanted to use gradient boosted trees. So gradient boosted trees are really nice for interpretability because they allow you to measure what are called feature importances. So you can measure how important were your input features in predicting a certain output. and so allowing in this way for interpretability of its of the model. And so what we did here is that we use as input the halo mass accretion history, feed it into a gradient boosted tree, and predicted as output the final mass profile, so the mass as a function of radius of different dark matter halos, in massive dark matter halos in the simulations. And so what you're seeing in this plot in the left panel is the importance of the inputs, so the mass as a function of scale factor of redshift of the mass accretion history, in predicting the mass of the halo within 0.2 of the virial radius, 0.3, 0.4, so all the way to the outskirts of the halo. And so if we zoom in one of these panels, you see that there are three most important timescales in predicting the final halo structure. The first timescale, the first peak in the feature importance, actually coincides with the time, with the formation time of the cluster. So this is basically the time at which the virialized part of these halos was formed, the early formation time. Then there's a second peak revealed by the gradient boosted trees, which actually coincides with the dynamical time of this halo. So this is basically material that has fallen into the halo and hasn't had the time yet to viralize inside the halo. And then the third time scale here is actually the time of the last major merger of the halo. And so what these results show is that there's really two components in the dark matter halo. One is the viralized, early formed material, and the second is a dynamically unrelaxed component made of dynamically infalling material, as well as the latest major mergers. And so this shows that basically in order to describe the structure of dark matter halos, we need to consider both of these components. So this is great, but it still requires gradient boosted trees have this ability to tell us basically which features, which input features are the most important in predicting your output, but it still requires humans to come up with features of the data. So it still required us to say, okay, we want to test which timescales of the mass accretion histories are most important in determining the final halo density structure. So it still has this limitation that it requires humans to come up with features of the data. So what we really wanted to do is to actually try to extract new knowledge from deep learning models and try to push what are conventionally known as black box networks, such as convolution neural networks, into this interpretable and explainable regime. So there was a very nice paper by Rabban and other collaborators in Zurich in 2020 that basically started thinking about, okay, how do humans learn? So what we typically do is that we have a bunch of data, say for example, particles moving in some sort of trajectories. And what we typically do is that we try to compress that data into a low dimensional, simple representation, so that if you ask me a question about that system, I can give you an answer to your query based only on the information in that representation. So in the example of particle trajectories, you would typically compress that data into the initial position and the velocity of the particle, so that if you ask me where will that particle be at some time t prime, I only need to know the initial position, the velocity, to give you an answer to that question. And so they basically try to translate this sort of, human learning schematic view into a neural network. So again, you start from your raw data and you want to compress it into a low dimensional latent representation. And this time that compression is done by a neural network. So that if you ask me, so that if I need to give you an answer given some query, I only use information from that latent representation. And again, the answer given the query and the latent representation is parameterized again by a neural network. And so what they showed in this paper is that SciNet is able to learn the relevant physical parameters for toy 1D problems, where you kind of already know the physical parameters that describe your system. And so they found that the latent matched basically the expected latent, the expected physical parameters. So what we wanted to do is extend this idea to a more complex case in cosmological simulations where we don't already know what the latent parameters should be. So what we wanted to do is to build what we call an interpretable variational encoder, this architecture framework for halo density profiles out to their outskirts. So our input in this case was the 3D density field at redshift 0 in a cosmological simulation. So the 3D density field in a subbox centered around the center of a dark matter halo. And we want to compress that information into a simple, low-dimensional latent representation. And that compression was done with a 3D convolution neural network that you see here. This is the encoder. And then given the latent representation, we wanted to predict rho, the density, as a function of any R, so the density profile. So by construction, all the information required to predict rho as a function of any R is contained within this low-dimensional, simple latent representation. And so this was work that was done with Hiranya Paris in Cambridge and Andrew Ponson at UCL in particular, that led to a couple of papers and of works that I'll be telling you about now. And so basically this model compression is really what enables this idea of explainability. So compressing all the information relevant to predict your output, so the density as a function of radius, into this low-dimensional latent representation. So let's have a little look in more detail at what this latent representation means, what it actually is. So again, we have the inputs, which is this 3-dimensional density field around the center of a halo. And you want to compress that with the encoder into this simple low-dimensional latent representation. And so the simplest latent space you can think about is just a set of independent Gaussians. And so what the encoder is actually doing is that it's predicting the mean and the standard deviation of each of these Gaussians. So imagine you choose a 4-dimensional latent space, your encoder basically predicts the mean and the standard deviation of each of these latent distributions for each halo. And then since you have a variational latent space, a probability distribution for your latent space, you can actually sample from this latent space, and then your decoder produces a range of possible density profiles, rho as a function of R, from each of these samples. So you see from the samples of the red star here, you produce the red profile, and from the samples, from the purple sample you produce. And so you basically have a range of possible realizations of the density profiles given samples in the latent space. Now, the key thing for making this latent space interpretable is that in machine learning language, the latent space needs to be disentangled. So what this means is that each of these latent parameters capture independent factors of variation in your profiles. And the way we impose this disentanglement is via the loss function that is optimized during training. So in the loss function, there's not only a predictive term that basically tries to force the network to give you accurate predictions for the density profiles, but it also has a term that tries to impose this disentanglement in latent space. So try to force the latent space to be as close as possible to independent Gaussians, so that the information within these latents is disentangled, so that there is independent factors of variation captured by each of these latents. Okay, Okay, so we trained our IVE to predict basically density profiles for broad range of halo masses from 10 to the 11 to 10 to the 14 solar masses over H and redshift 0. And here are just two examples of what the profiles for two individual dark matter halos look like. And so you can see again a band for the IVE predictions, the interpretable variational encoder prediction, because again, you can sample from the latent space, and this gives you a range of profiles. And so you see here that, you know, the IVE basically gives you a prediction for the density profiles that look smooth. It looks something like NFW up to R200, which is where the NFW profile was designed to predict, to describe density profiles. But we were actually interested in developing a model that goes beyond R200 into the halo outskirts, because the outskirts basically exhibit cosmologically interesting features that are related to the splashback radius. And because the splashback radius carries cosmological information related to the nature of dark matter and to modifications to gravity, we were interested in basically having a model that could predict the density profiles out to the 2 times R200, out to these halo outskirts. Okay, so once we have this trained model, how do we actually interpret this latent representation? So the way we interpret this latent representation is via mutual information. So mutual information is essentially, it's a bit like a correlation coefficient, but instead of just capturing the linear correlation between two variables, it actually captures the full statistical dependence between the two. So it captures both linear and non-linear correlations between two variables. And so we can actually measure the information content of the latent representation by measuring the mutual information between each latent and the density profile themselves. So we start off, let's say, with a 2-dimensional latent space, and so we see, okay, latent A has information about the density profiles on these radial scales, peaking at about 0.5, 0.3 of R200, and then has no information about the halo profile on the outskirts. Then we measure the mutual information between latent B and rho of R, and we see, okay, they share basically no information on these radial ranges here, but then latent B has lots of information about the density profile in the outskirts of the halo. We then add a third latent to our network, so a 3-dimensional, this time we train a 3-dimensional latent space, and we see, okay, the third latent has some additional information about the profile sort of close to the R200 boundary. And then when we add a fourth dimensional latent space, we see that basically this has no information about the profile throughout all radial ranges. And so the first thing you can tell from this is that you need is about the dimensionality of the problem. So you need 3 latent parameters to describe halo density profile up to their outskirts. And that these 3 latents have information, one about, you know, this inner region, one about the outer region, and one also close to R200. And since this work, we've actually extended, we've developed a mutual information estimator that I encourage you to go look at in this GitHub. It's publicly available, it's very well tested. It produces uncertainties and it's very robust. This was work led by Davide Piras. And so if you're interested in using these mutual information estimators, check out this paper and this GitHub repo. Okay, so we can actually go beyond this and try to explore a little bit more what these latents parameters mean. So what you can do, for example, is that you can fix 2 of the latents and systematically vary one latent to see what effects it has on the final density profiles. And you see, okay, latent A, which was the one containing this information about the sort of inner region of the profile, is basically controlling the normalization of this profile. So this is similar to one of the NFW parameters. So it's controlling the normalization of the density profile, as you can see here. Latent B, which is the one that contained a lot of information about the outskirts of the profile, is instead capturing basically the outer slope of these density profiles. So it's exactly this capturing how the slope changes, and so this flat splashback features that we were interested in capturing. And then latent C, you can see it's actually controlling the inner shape of the halo, and so something like is the concentration in the NFW profile. So you see the shape of the profile in the inner region. Okay, so can we actually, what we try to do is then see, okay, can we actually exploit this latent representation even beyond its original training task, right? So what we trained our neural network on was, remember, this 3D density structure of the halo at redshift 0. We encoded all that information into 3 latent parameters, which are sufficient and required to predict the density profile of the halo. Now we know, however, that the density structure of these halos is really a result of that complex nonlinear dynamics through the halo evolution history. And so does the latent space actually retain information about the origin of the halo density structure, and so about the halo evolution history of the halos? And so what we did here is that we looked back at the evolution history of these halos in the simulation and computed the mutual information, this time between the latents and the halo assembly histories. Although remember that the latents had no explicit information about the halo evolution history during training. They only know about the redshift 0 final density structure of the halo. And so what I'm showing you here on the top panel is the mutual information between the 2 most interesting latents, which are really the inner shape one, so similar to the concentration, and the outer shape one capturing the splashback feature. And so the top panel shows the mutual information between the latents and the mass as a function of redshift of the halos, whereas the bottom panel shows the mutual information again between the latents, and this time the mass accretion rate, so the rate of change of mass as a function of redshift. So if we start off with the inner shape latent, remember it's this one changing the shape of the profile in the inner region, we see that it has a lot of information about the early assembly history of the halo. So it has more and more information about the halo up until this redshifts, and then it loses information about the later time evolution of the halo. And this is basically consistent with the idea that the inner shape of the halo is a sort of, just like the NFW concentration, is related to the early phase assembly history of the halo. Instead, if we look at the outer shape latent, we see that it's basically insensitive to the most of the halo assembly history, so it has very little information about how the halo is assembling mass over time, but it has suddenly lots of information about the most recent rate of change in mass as a function of time. So basically the outer shape is mainly sensitive. Outer shape, which is described by a single degree of freedom, by a single parameter, is sensitive to the most recent accretion rate of the halos. So how does this match to a current sort of understanding of density profiles, where, as I said, basically the IVE recovers this known relation between the inner profile and the early assembly history, which was sort of first pointed out in 2002 by Luisa Wexler, showing this correlation between concentration, the NFW concentration, which is basically our inner shape latent, and the formation time of the halos. But the IVE also discovers something interesting about the autoprofile, and that is that you only need one parameter, one component to describe the shape of the density profiles in the outskirt, and then this is related to the most recent accretion rate of the halos. Okay, so what about substructures within host halos? So far we've talked about basically the overall parent halo and its density structure, but we know that one of the main lambda CDM predictions is also the presence of all these tiny substructures within the halos that you see, for example, in this video of the simulation, and that basically the properties of these substructures, their abundance and their shapes, can also tell us about the nature of dark matter. So with Giulia Despali in Bologna and Focus Springo here at MPA, we wanted to basically start looking at small-scale structure, and in particular, the most promising way to detect these small-scale structures within halos is via strong gravitational lensing. So with strong gravitational lensing, you basically have light coming from background galaxies that get distorted if in the middle there's a presence of a massive massive galaxy clusters that creates these distortion to the light rays going past this intervening galaxy. And if there are substructures within these within this lens, within the lens, you can actually detect these as basically density corrections to an otherwise smooth strong lensing feature. So on the right panels here, I'm showing you a detection from Simona Vigetti from 2012, showing you basically in this top panel what the classic sort of signal of the strong lensing Einstein rings, the model for that, the reconstructed source in the bottom left, and basically the detection of a subhalo, which is as a density correction over an otherwise smooth model. And these density corrections are basically, you know, 10 sigma detections, right? So they're really strongly detected subhalos on an otherwise smooth lens. And so then these kinds of detections can actually be used to infer subhalo properties, and which can in turn then exclude various different dark matter models. But the inferred subhalo properties depend strongly on the assumed density profiles of these subhalos, which are typically taken to be as standard NFWs, even though NFW profile was originally designed for, you know, relaxed main parent halos. And so what we did is that we basically wanted to reapply this IVE, but this time training it on the density profiles of the subhalos within R200, because that's the kind of radio range that is sensitive, that is relevant to these strong lensing detections. So we do a similar thing this time using the illustrious TNG 100 simulations. So we create input subboxes, this time again around the subhalo center. We feed it into our IVE to get a model for the density profiles of these subhalos. And this time we do it both for the gravity-only illustrious TNG simulations and the hydrodynamic simulations to capture the impact of baryonic effects on these density profiles. And so what do we find this time? We find again that there are three parameters, three latents needed to describe the density profiles. There's quite a strong hierarchy in the information content of these latents this time. You see here in pink the mutual information between the most relevant latent and again the density profile, and basically has information in particular on sort of 0.5 of our VIR. Then you have a second latent that has mainly information about what's happening towards the virial boundary of the halo, and then you have a third latent that has less information than the other two, but is still important to achieve accurate subhalo profiles, and this has information about this sort of dual mutual information curves, both on the inner region and in this mid-range region. And what you see is that for the model trained on the gravity only and on the hydro simulations, we have qualitatively the same parameters. This means that baryonic effects don't need to be captured with an independent parameter, an independent degree of freedom, but their effect can be captured within the same, qualitatively the same three parameters, or the same three latents. And again, you see that if you add a fourth latent, this latent D, this has no information basically about the density profile. Okay, so what are these three different latents? You basically have, again, one that is a normalization latent, and this is true for both the model trained on gravity only simulations and on the hydrodynamic simulations. Then you have one that is basically capturing somewhat the tidal truncation, which in our case actually exhibits a flattening in the profile because the density profile basically reaches the background value. And so you see this profile here reaches the background much earlier, so it's much more tidally truncated, whereas this darker pink one extend to larger radius, meaning that it had less tidal truncation. And you see again that the parameter sort of describes the same qualitative features in the gravity only and in the hydro. And then again, you have an inner shape profile here that is something like the concentration, both for the gravity only and for the hydro sims. Again, we can try to physically interpret these latents by looking at the information content with respect to the halo assembly history. And again, right, the network here knows nothing about the halo evolution history, is only trained on the redshift 0 subhalo density structure, yet it retains information about the evolution history of these halos. And so what we find is that the normalization latent has information about the mass as a function of redshift of the halo, up to basically the time at which on average, the subhalos fall into the main parent halo where they belong. Whereas for latent B, which is this truncation latent, is very sensitive to the formation history after the infall time. So after infalling into the main host halo, whereas again, the inner shape latent is mostly sensitive to the half mass formation time that is indicated here as a black vertical line. And so again, we have a physically interpretable subhalo density profile that is accurate and depends on parameters that we can physically understand, and then we can physically set priors on these. And so the next step is really to integrate this IVE model within strong gravitational lensing pipelines. Okay, so I don't have much time left, so I'm just gonna flash some work we did applying this IVE models to the halo mass function. This was work led by a PhD student, Lilian Guo at UCL, and also in collaboration with Hiranya Perez, Andrew Ponson, and Davide Piras. And I don't have time, but maybe we can discuss this in the panel discussion. Again, we basically applied our IVE network to the halo mass function to try to understand more the origin of non-universal information. And we found, some interesting results, which I encourage you to check out in these papers. In particular, we found that non-universal information is related to the late time linear growth and has also information about N effective. And I encourage you to look up this paper or ask me later in the discussion session. So I hope I've convinced you that this idea of interpretability and explainability in deep learning models can be achieved via model compression and then using information theoretic metrics such as mutual information to try to interpret what these latent parameters encode. And in particular, the IVE tries to disentangle these different physical effects into a minimal set of ingredients, and this led to new physical insight into some of the emergent logical structure properties such as density profiles and halo mass functions. So thanks a lot for listening, and I'm looking forward to the discussion in the conference.